So we're going to talk about model resource management techniques. And the idea is similar to what you heard today. As we go in the future, and it's basically the way that industry is going, models are getting bigger and bigger. And like you need to be able to somehow manage it to reduce the cost for deployment, especially. 4 years ago, every company was building a machine learning model. Basically, the idea was that build your own model, deploy it. All you needed was maybe a CPU or maybe a GPU, 810 GPU, like 20 gigabytes of RAM. You wouldn't have a machine learning model that's need 20 gigabytes of RAM. Like even Alex and all of this would run less than that. But now it has changed, right? So the idea is that models just getting bigger and bigger, and that's is proven at least right now by the scaling law. The more data, the more parameters you have, the better the accuracy of these models. So if you're dealing with scenarios like this, that your models are getting bigger, what could you do to reduce the cost of this product that you are building? So the first thing is just simply dimensional reduction, right? So before doing dimensional reduction, when you do EDA, especially if your data is tabular or your data has a specific set of features, what would you do? You basically select some features based on some domain knowledge that you have. You create some features, you basically do feature selections and so on, right? Now, the problem was that over time, you end up with building more and more features. What we learned was that if you have more features, build more features, you get a higher accuracy. So we ended up basically building features. And when you add features, it's kind of like exponential, the cost of basically adding these features. Now, how many of you have heard this before? If you do neural network, you don't need to do features engineering. You just pass everything to neural network and it learns it, right? So there's a big problem with that. The main problem is that is correct. Neural network will figure it out, especially the more layers that you have, it will figure out which features are bad. But when it comes at inference, when you need to load that model, what will happen here is that, so you will end up with, imagine you have this one layer and this has these nodes, okay? And let's say your neural network has learned, anytime data goes to this node and this node, it doesn't have any meaning. It basically sets the weights to really low, 0 almost. Over time, basically, these are connections, right? So neural, basically, the model learns that, okay, these nodes, I'm not going to use them for compute. That's how I do feature selection, kind of like an L1, basically, regularization. What happens is that despite the fact that weights on this node is almost 0, you will still have nodes, right? So you will still have nodes. That means you need to store those nodes. Nodes has cost of basically the space that they take. They also have degree or speed, because data still need to go through these nodes, right? So this is correct that neural network will do automatic feature selection, but they will reduce the speed at inference speed and increase the cost and the space you need basically to run that specific model. So I highly recommend you to avoid that assumption that, okay, you have a neural network, just pass everything to it, it will figure it out. Again, it does it, but later when you want to use that in production, you will end up with problems. Now, we talked before about dimensionally reduction and feature space. Let's look at one example, like embedding. So yes.
So how do we do in the case of dropouts? We manually have to set some parameter, if this node will be dropped, and in the second time, in the second hidden layer, it will be switched on. So how this will work in that?
So dropout technically, it's kind of like a Bernoulli process, like a Bernoulli distribution. Like everything, it's kind of like has a probability of mu being active, 1 minus mu being deactive. So in dropout, what you do, in every iteration, you build one network, which is called a thin network. A thin network, which is a network that if this is your network, in one operation, you don't see this and you don't see this. So this is a thin version. In next epoch, randomly, because this is the probability of a node being active is just a Bernoulli value, so it's random. In the next iteration, you might get this. So this one and this one is off, and so on. So when you do dropout, what happens over the number of time? Let's say you do 100 epochs. You basically build 100 thin network. The final result is an average over all of this, which is proven. Instead of actually doing this, you can approximate the impact of an average, like an expectation value over nodes to fall. What's the expected value of a Bernoulli? P. So every node has a chance of basically P to be on and off. So if you just simply build a network without dropout, you can apply the dropout later during the forward process. By basically what you do, if imagine you have a basically weight which is 100 without dropout, and based on your Bernoulli, there's basically P is 0.5, right? So you basically scale this 100 by 0.5 at the end, and that becomes your new weight. So dropout it's different because you are not optimizing for speed. You are not optimizing for you are not removing nodes. You just basically fluctuate between nodes because you want the model to be generalized and you don't want your model to memorize data. Versus here, when you let the model to decide what nodes to be in, what nodes not to be in, you basically, the model has the nodes, but these nodes never learn anything. It's always off. It's not random on and off. Does that answer? All right. So you all have built neural networks before, right? I assume you all have also worked with an embedding layer. So in embedding layer, what happens? So you have text, you tokenize it, you basically get some sort of like a vector representation, and you're passing it to an embedding layer, right? So the result of that embedding layer, after all this text comes through, will be a space like this, basically, an assumption, right? So, and this is like a 3D, right? So now imagine, imagine this. So if you have just one vector of numbers on top left, one dimension, all the points are on top of each other. If you go to 2 dimension, basically on the left, now this square is equivalent of that square that you have up there, but only some points will fall in. Now, if you go to 3 dimension, the number of points that will fall within that even gets less, goes lower. So when you do something like embedding, the more dimension that you have in your embedding, the better the learning. That's the idea, because you allow the model to learn better representation of the words. Almost, it's kind of like, it's not exactly, but almost it's kind of like every basically value within an embedding accounts for something about the data. So like, that's why if you do king minus man equal queen, right? Why? Because there's one dimension, one direction in the embedding that accounts for gender. One direction accounts for, I don't know, like a loyalty, right? Or royalty. So all of this basically tells you that more dimension is important, but then there's a huge cost that can basically impact your product later. Now, high dimensional problem is that basically if you, more dimension technically means better result, especially on training, but also means that you're probably going to overfit. On top of that, basically the distance grows more and more when you add dimension, and that's actually called concentration phenomenon for Euclidean distance. What does that concentration phenomenon says that if you have 2 vectors, right, which has 3 values, and you calculate Euclidean distance, the distance, if they are similar to each other, the distance is small. The more dimension you add to a vector, the Euclidean distance increases. So if you have 2 vectors that are technically close to each other, the more dimension you have, they end up becoming further from each other. So especially if you're doing a techniques or model type of model, this distance based, having more dimension is actually not beneficial because by default they are far from each other. Okay. So now, why more features is not good? Because you end up with redundant features, irrelevant features. You have some sort of like a multicollinearity. You have more noise. It's hard to interpret or visualize, basically, and hard to store and process this data. There is a basically performance algorithm. The idea here is that for every model, there is an optimal number of features that gives you the highest score. And beyond that, the model performance degree doesn't matter what you add. You know, that's a theory. And that's why you technically do some sort of like a feature engineering to figure out what's that optimal number. So this is an example of 1D. As you go to 2D, this is basically what happens, and it's basically what we talked about. Now, there's another term called Hughes effect. Hughes effect basically says that the more feature that you have, the larger the search space. You need to always be aware of search space. Search space is the space that your algorithm, your neural network, actively will search through to find the optimal values. The larger this space, the slower the process, and the harder for your neural network to go towards some sort of like a global and not get stuck into the first local optimum. All right, so you need to always keep that in mind. So how do we deal with that? Well, so far, manual dimensional reduction, you do feature engineering, and especially we had a class over those, the different techniques that you can use to reduce the dimensions, right? But there's a problem with those types of basically feature exploration or manual dimension reduction is that lots of data that you see, you have high number of basic dimension. If you think about images, images are not small, they get actually larger and larger every day. It's the number of pixels basically. Videos, signals, it's not that easy to do manual feature selection or basically dimensional reduction in a manual way. But you also need to know that I need to reduce the dimension because it's costly. Why do we reduce the dimension? For storage, that's the first thing. You know, the more dimension you have, the higher the cost of the storage. Computation, consistency, visualization, and all of this basically needs some technique like some automated engineering or some basically manual feature selection. We're not going to talk about manual feature selection, but we're going to focus on basically algorithmic dimensional reduction. So the first technique is linear dimensional reduction, which it's kind of like a straightforward process. It's like if you have a k dimension, or sorry, if you have n dimension and you want to from n to go to k, you just find a linear process to map data to lower dimension. An example of this is this. So here you have fn values, and that's one data point. From that, you can map it to just one dimension in a linear way, right? Where have you seen something like this before? PCA. Every principal component, it's a linear dimensional reduction technique by itself, because you map from all dimension into one principal component. So there are other techniques on like a linear, which is done, or dimensional reduction. First one is linear discriminant analysis, LDA, which by default, it's some sort of classification technique, right? It's a generative classification technique. And what it does, it focuses on maximizing the separation between classes by assigning low, almost zero weights to the dimensions that are not important. Really similar also to like a L1 regularization. Then you have PLS, partial least square, which focuses on basically selecting features that maximizes the correlation between the target, the data, and the target. You also have seen PCA, which basically focuses on, you know, just mapping the data that exists in linear higher dimension to linear lower dimension. So I'm not going to hover over PCA much, but you're all probably aware that what PCA does is kind of like you build one, you have the data, you map it on this one linear dimension using what you saw above, After you found this, you're like, okay, I put this one here, perpendicular. Now I map everything on this. You do that, and then you bring another one. So find the next perpendicular, right? So you keep rotating this axis and adding dimension and map the data to, right? By doing so, you have basically two focuses, depending on what algorithm you use. Both gives you the same answer. One algorithm focuses on every time you basically project the data on this vector, your goal is to maximize the variance explained. That means if points fall in here and all of them are condensed, that's not good. You minimize the projection variance. You want them to be like kind of sparse, far from each other. Why? Because if you condense them, then you lose some information. So you want them to be far. The second technique in PCA focuses on reducing the projection distance. That means if points are here and I project them here, I want the principal component that I project on to be as close as possible to the original location of the data. Right? And these two technically are the same thing, give you exact same answers. So, read past that. What are the strengths and weaknesses of PCA? Well, a strength is versatile technique, it's fast. It basically offers a series of techniques. You can even use kernel PCA, which helps you with non-linearity. Technically, PCA should be linear, but you can apply a kernel trick to basically account for non-linear data. But what are the weaknesses? First, it's not interpretable. Right? That means if you use PCA if you're building a product that the reason, like let's say you have a product that makes a classification decision for a patient. And the doctor come back and says that, okay, why this patient doesn't have, why you say they don't have this disease? If you have used PCA, what will happen is that you can only respond with respect to principal components, which every principal component, it's a mapping from all dimension to it, right? So it's kind of hard for you to try to trace that back. So it's not interpretable. And also you need to always figure out that threshold that you want, how many principal component you're going to keep or drop. So it has all sorts of basic issues. Now, there's an alternative techniques that you can use that are much better than PCA in practice. If we look at unsupervised, the first one is latent semantic indexing or analysis, LSI or LSA, which are singular value decomposition based techniques. Okay, have you heard of those techniques before, LSI or LSA? Yeah? Okay, we do talk about it. The next one is independent component analysis, ICA. Then you have matrix factorization, which is technically some sort of like a non-negative matrix factorization or NMF. And then we have the LDA, which we talked about. Now, so the first one, LSI and LSA, those two techniques are singular value decomposition based. If you work or go for an interview of any companies that they do recommendation system, they always want to know that if you can work with SVD. The idea is that if you have a data, you can present it, but if not non-square data, if you do singular value decomposition, you can present it into three components, basically submatrices. And these matrices will carry different information about the original data. The example that I always use that, if you pick number 12, and I ask you randomly, can you describe number 12? What would you say? Just number 12, describe it.
That's the movies.
No, number 12, just number 12.
It comes after 11 and before 30.
What would you say? Yeah.
I would just say it's a mathematical number which is present in the.
Right. What would you say? Number 12. How would you describe number 12? Doesn't matter which one of you.
2 multiply 3.
2 times 3. What else? Doesn't. So what's going on here? A number, simple number, everyone is going to describe it differently. Why? Because you can describe it differently. right? He described it correctly. 2 times 2 times 3. Why? Because you basically break down the number into the main components of these numbers. Now, everyone will understand this, versus everyone will describe it differently if you say number 12. When it comes to data, the general data has all sorts of meanings. But if you are able to break down that data into its constituent matrices, they will give you the prime, basically, information you need to solve instead of trying to focus on this. So when you work with recommendation system, this type of model, you focus on breaking down the data, because especially anytime the data has some sort of like a relationship between customers and product, you always do SVD. Because imagine you have this matrix, customer on the rows, columns are the basically products. If you do SVD, the new matrices that you get, one of them becomes customer versus category. The other one becomes product versus category by default, because the product that are in the same category, like a kitchen appliances, by default group together. And the one in the center becomes like the importance of every category. So when companies want to do a recommendation system, and you're like a new customer comes to the market, to your platform, and you're like, I don't know anything about this person. What should I recommend? I'm not going to look at this too. I'm going to go to here. Which product has the highest singular values? That's category. From that category, I go to product to category matrix. Which product within that category has the highest? So when you go on first time you go on Netflix, like imagine right now they ask you that, select you some top movies that you think they use it to generate that. But before that, you have this basically rows shows, for example, action movies, shows top action movies, horror movies, and so on. As soon as you click, like a comeback an hour later, that has changed. Because they know that, okay, you clicked on this movie is similar to this one, and so on. So that changes. So SVD is one of the techniques that highly basically capable for breaking down user versus product.
So how do we decide which data is important to us? Like, we cannot break whole data set into like multiple matrices, right? Since it's the trade-offs between size and the cost.
So the types of data also tells you what type of dimensional reduction you can use. If you work with any data that every row is an individual, it's kind of like an IID. Every row is an individual customer, individual patient, then you can do something like SVD. If you work with type of data that's kind of like an image, text, and stuff like that, then you're not going to go for what I was saying. But LSI and LSA in basically document indexing is when you have a lots of document and you want to group them, cluster them together and based on similarity. So if you do SVD, basically becomes document to topic, word to document, document to topic, and topics basically. And you figure out like how to do it. So the next one is ICA, which in practice is better than PCA for so many reasons which we're going to talk about. So in PCA, your goal is to reduce correlation, right? You purposely select principal components that they are uncorrelated. There's zero correlation, perpendicular to each other. So your goal is to reduce the correlation. In ICA, on the other end, your goal is to reduce the independency of the features. Okay, those two are different. But let's see if you can say the difference. What's the difference between two features that are correlated versus two features that are dependent? What's the difference between correlation versus dependency?
Dependency doesn't interact with those two features. For example, if A increases, but like that doesn't affect the increase or decreaseness in the feature. I would say that would be.
Okay, what else?
Dependency means causation, correlation doesn't mean causation.
Dependency means causation. It's a bold statement. Anyone else? So if you go to a class, because I force you, we will have a attendance. Is that correlation or is that dependence?
Dependence.
Is dependence. If you go to class because the weather is good, is that correlation or dependency? So let's ask you, if you register for a class for MLOPs in general, is that correlation or dependency versus if you come to the class because the weather was good? Which one is correlation, which one is dependency? You register for a class because it's correlated with something that you want. You think that it improves something. You come to a class because it depended on the weather, right? It's kind of like it was a good weather or worse. There's a famous article that the famous expression about the ice cream and chocolate in, I think it's like in Finland, right? Something like that. I don't know if you have heard of it or not. Anyway, so we're going to talk about this. Also, ICA addresses high order dependence. Now, what's high order dependence? A and B basically have dependency given C. That comes in network. So if you have A and you have B, right, and you have C here. In PCA, you will say A and C are not correlated to each other. There's no relationship between them. In ICA, it basically says that A depends on C, given B as a connection. Right? So that's a higher order dependency. So how does ICA works? So ICA basically is focusing on kind of like a hidden signals. You basically say that any data basically consists of series of signal S1 through Sn. Okay, and those are like a hidden signals that you want to recover. So, and good example here is that in the class, everyone is talking, and we have this Zoom is recording, right? How could I separate individual voices and isolate them from the other ones? That's what ICA does. ICA basically says that all these voices together are mixed signal, but this mixed signal is basically compound of individual signals which have some sort of like a mixing coefficients. A is a mixing coefficient matrix times those individual signals which we don't have becomes the actual audio that we have. So if you want to reduce the dimension, or if you want to basically to select a specific component music instrument from an basically song, you need to recover S, and then from S you can basically pick whatever is important for your data. Okay, so that's the idea of ICA. And again, PCA just focuses on correlation. ICA does correlation, higher order dependence. All components treated fairly is not orthogonal. All components treated fairly. Can anyone know why PCA doesn't treat everything fairly?
Because one axis is fixed, it has to be like.
Yes, if I have this data and I bring the first principal component and I map everything on it, correct? This component by default gets the maximum variance. Where can I put the second component? Only perpendicular. So let's say it doesn't matter here. Let's say here. Now everything will maps like that. And next one, so on. So as you go through components, because of this forcing to be perpendicular and you rotate it, the amount of data that they receive, the variance they will have becomes smaller and smaller. So by default, they are doomed to have no information as the number of PCA principal component increases. So it doesn't treat them fairly. In IC, that's not the case. So it always looks like a scary movie. So this is next one, non-negative matrix factorization. So the idea here is that we want to reduce the dimension of the data by breaking it down into two non-negative matrices. So if X is your original data, X is basically constituted of two non-negative basically matrices. If you can recover these two, then you have X. So what's the benefit of this? They don't need to have same dimension, right? They could have a lower dimension also. That the multiplication goes to that dimension. So that for dimensional reduction technique. This is similar to what you probably do in LoRa, right? LoRa technique and LLMs, you find two matrices A and B, where the basically dimension is small. So what you also can see that on PCA on the left, you reduce the dimension, but the quality of images, lower dimension, are not good. Versus in ICA, you can still detect the in NML, you can still detect the faces, right? Because again, it's just kind of like it captures better or higher quality amount of information. So if you do with like images, NMF is more common to use than something like PC. So now, all of this brings us to one thing: mobile, IoT, and similar use cases. So why mobile and IoT? Why do we want in this class to learn about mobiles or IoTs? What's your thought? Yeah.
Is it because of edge device computing and it doesn't have like a lot of compute power and that's small device?
The edge device is a mobile device, correct? But why? Well, like, why is it important to learn about it?
Because we have to know how much we should like compress the data in order to get it.
Okay, that's one. Latency, good one. Yeah. Is that all correct? What else? Like if you go work for a company and says that we only build for IoT, right? Why do you think they do that? Privacy, right? Lots of time you build products that they need to be air gapped, they need to be isolated from outside. Lots of companies are like that. Any companies that does security, it's IoT types of deployment, because those companies work in the like a domain that whatever you build should, if I run it, it should run in my environment, should stay there, right? I personally always, like from the day that I graduated in Northeastern, just worked in basically regularity environment. 7 years in cybersecurity, everything we built was just supposed to run only on this computer. No internet connection, no interaction, no data sends out. Your model needs to run, updates itself, and so on, so on. We have a group here, they do federated learning, so I'm interested to see their work later. And now the company that I work, it's aerospace defense, which we can imagine. Everything we built, when we give it to a customer, they take it, they test it for all sort of security matters. And when they run it, that's it. We don't see anything about that data, that model. We just might hear like a word of mouth, okay, on a call that this works, this doesn't work. What direction maybe the tailor is that, okay, you missed this parts. You missed this types of data. That's it. You bring that knowledge and you try to build synthetic data, go fix it, iterate with customers. It's common, especially the way the industry goes. Lots of times, privacy is becoming more concern these days, right? But also cost. Your friends, they said correct things. Cost, like maybe like 2 years ago, or even now, lots of companies, GPUs, and trying to deploy to the cloud and stuff like that. But over time, companies are also learning that I need a smaller model. I need to be able to run it on a whatever I have. I can't buy GPU for my entire organization. And if they need to work with models, how could we build smaller models? So first thing is that your cell phones getting stronger and stronger every day, right? So if you think about it, the GPU that your cell phone has is probably faster than the GPU that we had in 2012. In like an industry level GPU. It's like the compute that you get from your cell phone. So cell phones getting stronger. There's always demand to move from cloud to on device. It's cost effective because if you build a model that runs on this cell phone or on this computer, I don't pay for anything, right? No, I don't pay for the compute. I don't pay for the internet or electricity or anything. So if your company can build something that's basically edge-based, you don't need to worry about anything deployment related. You just deploy it, and then it runs on the customer environment. And then also compliances with privacy regulations. So now, if you want to generate real-time prediction means that it's quick answer. A good example, self-driving cars. Every self-driving cars has a stack of GPUs in those. Probably you have seen some of those, right? So why? Because you can't wait for data to go to cloud to decide, should I brake or should I turn left or right? I need right now answer. So you need to build something that, it can utilize certain types of GPUs and runs basically on that on-prem. That's not the best example because you're still using your GPUs, but not cloud deployment. So do you think it's faster to serve on the server or on a device? On the device, right? It's faster because you don't need to communicate, right? It's just, you just send the data. If you deal with on cloud servers, there are lots of pros. Lots of compute capacity, scalable hardware, model complexity can be increases, easy to add new features. Why easy to add new features? Because if it's on cloud, everyone uses your model on cloud. You build another model or add something and you do some sort of like a canary deployment and release the model to everyone. Versus if you build on-prem edge device, if you have a new update, you need to release an update. And you need to hope for customers to install the update. If someone doesn't install the update, then you have issues. And lots of time in, like, let's say you build something and you're selling it to Northeastern, Boston University, and all other universities using your software. Let's say you have a new release. And as soon as you release it, what you will notice is that there will be first about 1 month to 2 months before IT even decides on installing that release. Then there will be this long delay between different universities. So one university maybe they have a better IT system, they install it. As time goes, you still have universities that they're on the older version. So what's the problem over there? What else? Inconsistency is one. What else? You need to manage multiple model versions constantly, because everyone could be on a different version, right? But what's the cons of inference on cloud services? Well, it's timely, especially if you need something quick, and the cost is, we're not talking about the cost here. But if it's timely, that means you need to communicate to the cloud. On device, it has its own pros. It's fast, it's performant, basically. You work whatever you get. It doesn't need network connectivity. No end-to-end connection, basically, no communication, no MQTT, no protobuf data need to go out. But what are the cons? Less capacity, tight resource constraint. And that's important to remember. If you are building for on-device, you need to know what is the minimum resource available, what's the maximum resource available in the market. So if you're building an app for cell phones, iOS and Android, you need to have an idea, okay, if I build this model, and everyone is going to be able to install it, what is the worst case cell phone out there that they're going to install my app? How much compute? Do they have even the computer, do they have the storage to install? What's the best model out there? Best GPU or iPhone, for example. So you need to understand this resource constraints. Either your model is going to be fixed, I'm targeting the worst case scenario, so I build a model for that size, or you have a model that basically kind of doing dynamic resource basically utilization. So you need to account for those if you do on-device inference. Any question on that? All right. So there are some like tools out there that you can use for on-prem deployment. MLKit, Core ML, TensorFlow Lite, PyTorch. I think PyTorch Lite also is called, or PyTorch Mobile, something like that. Those are basically what they do after you develop a neural network model, and this is after you develop. And you'd save your neural network. You use, for example, if it's a TensorFlow based, you use TensorFlow Lite. And what you do, it converts the model to basically a smaller, light version by doing certain quantizations. That way, that model could run on basically edge devices. Otherwise, you cannot just pick the large model and run it on basically on-prem device. So now that brings us to quantization. But okay, before we start, I'm going to give you a break, and then we're going to continue from there. All right. Okay, so today our guest basically spoke about quantization, and you got some exposure to it. Now we want to go more in details about quantization and how different types of quantization work and when to use which. Okay. So the main idea behind quantization is that when you work with your models, especially your neural networks, PyTorch, TensorFlow, by default, the weight or the parameters are stored in float 32. Okay. The idea of quantization is that, let's say, for example, you want to go from float 32 to integer 4. So if you look at the curve, in float 32, the points, like every 2 points, are they have some distance from each other. When you go to integer 4, the same points will get the same value in integer 4. So that's the idea of quantization. You kind of become something of like a bucketization grouping of numbers based on the range that they will fall into. Now, when we look at the neural networks, there are different things that you can quantize for. You have weights, you have biases, and you have your basically activation map, which is the output of every neuron, right? We also technically, these are things that we quantize. We also have something like the attention, which Philip talked about, or the output of the model, like the softmax. Those are actually, you never quantize, you never touch those, because those are the values or the basically the parameters or values that the precision is super important. So when you talk about quantization, your focus is on weight, bias, and activation maps. Now, there are some benefits with quantization which we talked about. It's basically reduces the model size, reduces the computational resources that you need, and makes the model run faster, and basically it uses less or lower precision. Okay, so let's look at an example here. So if you there's this like a mobile net. It was one of the earliest basically neural network models that even back then, like that, it was like a couple of millions basically parameters, was really expensive. But the idea here is that on the orange you have float, green is the 8-bit quantization. So what you can see here is that the runtime on the model in order to get the same accuracy level. So with 8-bit quantization, for example, around 50, if you see the green on 50, has higher accuracy than the orange 50. So that quantization basically gives you here in this example, give you a better accuracy, and it basically has a lower runtime, lower basically time that occurred for the model to run. So all of this basically tells you that it has benefits like a faster compute, low memory bandwidth, lower power. It supports CPU, DSP, NPU, TPU. So if you want to work on TPU, you always need to quantize your models. They need to be quantized for TPU. We work especially with what Google basically provides. Another way of looking at quantization is you shrink basically, or basically bucketize, as we say, the values. But it's not just about bucketizing the values, it's also about changing the dynamic range the values have. So the original values goes from here to here, basically, that's actually the int 8, sorry, float 32 goes from here to here. In int 8, it basically goes from there to there. So the range from -27 to 127, what does that tell you? There are only 256 numbers in between in int 8. In float 32, you can see how many numbers you can find over there, right? So it changes the dynamic range, it bucketizes the data, and you need less number to represent your data in general. Okay, so that's the idea of the quantization. Now, before we delve deeper in quantization, let's talk about representation. So when you try to represent numbers or values in basically computer language, so what we do, we use something called bits, right? So if you think about the float 16, what does that mean? You basically have 16 values, like 16 bits basically that you store. It always starts with this. On the left side, you have the sign, which is 1 bit. Then you have exponent. Then you have mantissa, right? So the difference between different representation is the difference between number of exponent bits and the number of mantissa bits. So in float 16, for example, again, you count it. The number of squares are 16. Those are the 16 bits. Among these 16 bits, the mantissa are the precision ones, the one that become really precise. The exponent and sign becomes the earlier values. Now, if you compare, if you want to do one calculation, so just one random example here we have. So here, whatever value you see in the square is the value of that bit. So the sign is 0. So you calculate it using the following equation: -1 to the power of whatever is in the sign. So you have -1 to the power of 0, right? Times. Then you go to exponent. In order to understand the value of exponent, you need to calculate two things: an XP value and a bias value. So XP value is among these exponent bits, which one is activated? The first one. An exponent bit basically from right go to the power of 0 to the power of 1 to the power and so on. So here the last one is 2 to the power of 4 and is activated. So what will be the value? Becomes exponent 2 to the power of 4 becomes 16. Then you have bias. Bias is 2 to the power of b minus 1. B stands for the bit, right? So 2 to the power of b minus 1 to the power of how many bits you have in exponent 5? 2 to the power of 5 minus 1, or 2 to the power of 4, minus 1, total 15. 16 minus 15 becomes 1. 1 becomes the 2 to the power of 1. So when you try to represent this number. So minus 1 to the power of 0 times 2 to the power of 1. Plus. Then you go to mantissa. In mantissa, basically, the equation is like this. 2 to the power of basically 0 here. This one is, so if you think about it, so you have 2 to the power of, which one is accurate? -1, 2 to the power of -4, 2 to the power of -7. That total becomes 0.5, whatever it is, plus 2 to the power of 0 times 2 to the power of 1 times that. That becomes this number. So the representation of this number in float 16 is that those bits basically, that vector. Now, if you take that further, compare it to float 32. Float 32 means you need 32 bits to represent every number, correct? So we have 0, we have basically 1, 2, 3, 4, 5, 8, and the rest of it basically goes to Mantis. So the main difference here is that between float 32 and float 16, the exponent from 8 goes to 5, okay, and the Mantisa, not wrong, the remaining of that becomes like, that's 9, 32, 23, goes to, how many we have here, 5, 10, right? So you see the number of Mantisa basically that drops, and also the number of exponent that we drop. So this becomes higher precision representation of the same value. So this value, as original value, in float 32 will be stored this way. In floats, basically 16 will be stored this way. Does that make sense? Yeah.
How did we got the extra 1 bits on the Mantisa for 32 bits?
Which extra 1 bit?
So we have those extra ones in the end of the blue bits, right? So is it just an example, or you converted it?
No, this is actual number converted, but yeah. We're not gonna go to details of like which one becomes on and off, but it's just, that's a binary, right? But that becomes the total representation. So now, so another way is that, so if you think about the original number 75505, and you can represent it also in this form using 64-bit, the representation is the same thing. When you go to 32-bit, there is a slight change in the representation. On the right is the representation. If you go to that original number to 16-bit, the representation becomes 0. So see the difference of how you quantize, how you go down from 64 to 32 to 16. For that number, you don't have a representation. Now, the other thing we're going to talk about, so today you heard about different types of precisions. So float 32 is a default you get on your neural networks. And float 32 basically means that between numbers, you have small distance between 2 points. And that means you have low distance, you have high precision. So when the distance are small, that means you have a high precision, right? Because precision means that if you think about all this like floating points that you have. So 2 points that are closer to each other, the precision, that means you have a much higher precision in the value, actual value of the number. Now, if you go to, so this is called brain float 16, brain float 16, BF16. So if you go to BF16, if I'm not wrong, someone asked a question about, you asked, right? About BF16. So your question was, when I go from float 32 to float 16, all of a sudden, basically my model doesn't train it. I start getting it dynamics. But if I go to BF16, I don't have problem with model training, but the accuracy basically drops. So one of the explanation for something like that could be, when you go from float 32 to float 16, what happens? You reduce the dynamic range, right? But if you go to brain float 16, you keep same dynamic range. You just reduce the amount of basically precision or basically floating point that you have. So you don't change the range, you keep the range. In the other one, basically you squeeze the range. So you kind of destabilize your model during your training. And then if you go to integer 8, basically as you can see this funnel, the range, the dynamic range of these values becomes smaller, smaller, and basically here it becomes only it can tell you from min to max how many points you can, how many numbers you can fit there. The last one again, from minus 127 to 127, how many numbers you get? 256. Everything will be presented in 256 numbers. As you go up, you get more range, you get more values, right? So that's why when you train models, when these weights are in high precision, there is a reason for that, because the model learned by changing the last bits, it can make a different prediction. It can has a different impacts. When you go quantize, if you just simply go cut, for example, the last precision, that's why the accuracy of models drops, because the model needed those last bits during forward pass to make a prediction, right? And it will have this domino effect if you keep cutting all this, precision values. So now the next thing is the memory constraints. So it's not the easiest way for you to see. Let's just start with the example. Let's say you have a model has 70 billion parameters. And your first question is that how much memory do I need for this model? So there's a formula, number of bits divided by 8 times number of parameters. So if your model is in 64 bits, 64 divided by 8 times 70 billion, you need 560 gigabyte of memory. If you go to 32 bit, you need 280 gigabytes of memory. If you go to 16 bit, you need 140 gigabytes of memory. So that gives you some sense when you try to figure out which model to use, what GPUs I have access to. You can simply figure out by looking at how many parameters it has, what's it's stored in, can I run it or not? Can I use my GPU basically for it or not? Any question on those? All right. So let's go back again to quantization. So we say that quantization is kind of like an idea of reducing the precisions by bucketizing the values. So from two closed number, you go to a bucket because so that this bucket carries this specific range. Maybe from 2 to 3, any numbers that you had before will fall in that bucket. Right? So that becomes the idea. Now, and in another example, if you do quantization, the original image on the left, on the right, if you don't focus when you do quantization, you don't see the difference. But if you focus on the quantized image, you will see the blurry pixels. Is why? Because you cut the range of values. So maybe it's by naked eye, it's not easy to see the difference between two images. But for prediction, for the model perspective, it's easy to detect, okay, there's something is different about this data. Now, let's talk about common data types. So float 16, we should start over there. Basically, we said that, float 32, we first say that that's you have 23 bits, you have 8 exponents, and you have 1 sign. When you go to float 16, it becomes 1 bit, 5 exponent, and then becomes 10 bytes, right? So if you go to brain float 16, basically, what will happen here is that the range remained the same, but so the range remained the same because the exponent remained the same, but the mantissa decreases, right? So from 8, you remain to 8 exponent bits, but the mantissa from 23 went to 7 bits. So you keep the same range of values, but you basically quantize the values or the rate, basically the parameters. Then if you go to int 8 on the other end, which you can see that there is no exponent component. So in integer 8, you don't have exponent basically bits, you only have your sign bits and you have the mantissa bits. So that tells you how much information you will lose if you go from something to basically a float like that to integer. Now, the question is always like, if I quantize, what will be quantized? Like what will be impacted by this process? So you have static parameters, which are the fixed parameters of what you learn, weights and biases. You have dynamic parameters, which dynamic parameters means that anything that during the model run will be calculated. The output of layers, output of nodes, activations. And then you have the computation, like that overall transformation process. This will be impacted by quantization. So there is always a trade-off when you quantize. You will lose accuracies. You gain performance, you lose accuracies. You know, like or whatever metric basically your model has. And again, in some rare cases, the model has actually gained some accuracies. And this is just example of that. So mobile net, for example, on the bottom, the original mobile net has 72 accuracy, and then you quantize it, and basically you have a lower accuracy, or maybe accuracy versus model size. Sorry. So on top, you have accuracy almost original is 72, quantized is almost 72, really close to 72. But the amount of memory, so model size is, for the original one is 20 gigabytes probably, and for the other one is probably like 10 gigabytes. So you reduce the size of the model, almost you have the same accuracy. Now it's kind of like an older, basically image. This is a quantization are much better. Now, I'm going to talk about types of quantization. Okay. So first one is symmetric quantization. So the idea is that, so symmetric quantization basically means that if you want to mirror around certain basically values. Here we do 0. So you pick 0 as a center, and you basically, your goal is that to ensure that 0 in float 32 remains 0 in whatever basically range that you, or whatever quantization basically point you go to. You go from float 32 to int 8, you want 0 in float 32 to remain 0 in int 8. So that's the idea of symmetric quantization. Now, one of the technique for symmetric quantization is abs max, basically. So the idea of absolute max basically technique is that if you have this vector, so this is a vector of this numbers that you have, you will find the largest value, and you call it alpha. So the largest value, absolute maximum basically, is 10.8. Now, what you basically do, you account from minus 10.8 to plus 10.8, minus alpha to alpha as your range. Okay, using the maximum value within a vector, you create a range, dynamic range, minus 10.8 to plus 10.8. All points will fall within this range. Then you quantize to whatever dimension here is int 8 basic. But you enforcing that 0 be basically 0 in from float 32 to be the same 0 in the int 8. So what technically we did is we create a, so think about this, you have these numbers, let's say this is the original number. And they're increasing by positive. You find the largest, and let's say 0 was here. You find the largest, because you want this to be symmetric, you find if this is the largest, identical largest negative, and you connect it. Now this range is symmetric. Exact value distance from left to right. Then you map this in a symmetric way. So that's why you find the maximum, convert the maximum to minimum to find symmetric range between minus alpha to alpha, and then you convert that to int 8. Now, how does the conversion happens? This is the equation for conversion. So there's a, I don't know if you heard today, he mentioned that, Philip mentioned a scaling factor. S is the scale factor. In abs max, S is calculated as is 2 to the power of b minus 1, which is the bits, number of bits, minus 1 divided by alpha, and alpha was the maximum value within the vector or within the matrix that you are trying to quantize. And then after you find S, you multiply every number, every data point that you have by S and round it. That becomes the quantized version using apps max. So that means in the previous example that we saw, what's the largest value? 10.8. That's our alpha. What dimension we're quantizing to? Integer 8. So what do we know about integer 8? 2 to the power of 8 minus 1 minus 1, 127. Right? Correct? So 127 divided by 10.8, 11.76 is your scaling factor. Now for every number or the entire vector, multiply the vector by that scaling factor and round it, that becomes quantized vector basically. If you want to convert it back to original, you need to multiply it by 1 over S basically. So this technique is symmetric apps max quantization. So now, what about asymmetric quantization? Like what if we don't have that symmetric range basically? So the idea here is that in asymmetric, you find the highest and you find the lowest. So highest here is 10.8, lowest is minus 7.59. So you create a range from highest to lowest. Sorry, from lowest to highest, right? So basically that means if you have a vector, and let's say your vector wasn't sorted, you sort the vector, this becomes the lowest, let's say this is 0, and this becomes the highest. So the first thing you see is that this is not basically symmetric anymore, it's not mirrored around 0. And when you convert it to other basically precision or other data type, 0 location, as the line shows you, has moved also, shifted. So basically that means 0 in there, it's not exactly the same place as in A. So, and this is the equation for asymmetric quantization. So here basically we want to go to int 8. So what you see on S scaling factor is 128 minus 127. Or this is technically the same as 127 minus 128. It doesn't matter how you calculate it. Right? So that becomes technically 256 divided by alpha minus beta. What was alpha? What was alpha? 10.8. What was beta? Minus 7.59. So you do that. You find the range. And then you multiply the scaling factor times beta minus this, that becomes Z, you're finding the 0 point. You use the S and 0 point and the original data to find the quantized version. So if you hear symmetric quantization, it's kind of like a more straightforward, versus asymmetric quantization, this is a technique that you use. Okay. So, and this is just another representation of symmetric versus asymmetric. In both scenarios, you go to 128 to 128. That means you go to basically to integer 8. The difference that you see in symmetric quantization, 0 remains 0. In asymmetric quantization, 0 becomes minus 23. But the range max remains the same thing basically. Okay. So now, the next thing is range mapping and clipping. And I think Philip also kind of talked about the idea of like outliers. But the idea is that if you're looking at a matrix or a vector that you have and you want to quantize, what if one value is so large in compared to the rest of those? So if you have an outlier like that, what will happen is when you're looking at the numbers, your outlier is basically at the end and the far right, but every other data point, because they're really smaller than compared to outlier, they're so close to each other. So that means everything when you use integer 8 will fall to one number. And that outlier basically becomes 127, the max. So if you have a range of numbers, one is here, one value is here, and the rest are kind of like this. Technically, these are far from each other, but because the scaling compared to this one, they are so close. So when you do int 8 quantization, all of this will map to one bucket, or not some bucket. So then they all lose their meaning. So when you deal with something like that, you need to do some sort of like a dynamic range, or basically range clipping. Range clipping, the technique that is common in industry is that you come up with a range, for example, -5 to 5, it's common. And what you basically say is that if I have outliers, I ignore it for now. I assume my range is from -5 to 5. Everything will be mapped with respect to -5 to 5 as a range. Anything outside of -5 or +5 after, we always by default map to highest or lowest. So that means if you have this one here, which is the highest, you ignore it for now. You just focus on this range. Using this range, you get maybe like this beats. So in this beats, let's say these two go here, this one goes here, these two go here, and these two go here. And because you go to int 8, you know int 8 by default is from 127 to -127, for example. Then you say maximum will be assigned to 127. And if there was a minimum, I will assign it to you. Doesn't matter how many outside of this range I have, I will always assign them to last or to the first, the smallest number. And so this is a really common technique that's being used. Now, there are some problems with this. So actually, first let's go to that. There's some comment with this problem. Some problem with this technique. So think about this original vector that you have. You have one outliers, right? So if you use simply min-max basically quantization, what you basically will get is there is almost no error on the outlier side because 999 is the max, would convert it to the same thing. But you get high error on for example, the first one, as we see. But if you do the reverse, if you do some sort of like a range, dynamic range, like a -5 to 5 or percentile basically range, what will happen here is that you get a smaller conversion error on these numbers, but you get a higher error on these numbers, the outliers basically. So it comes, you see that there's a pros and cons. You need to figure out the impact of getting high error on your outliers versus getting a high error on the smaller values in your computation. And you can decide which technique is more important. So the idea of calibration is that you either select -5 to 5, or basically you dynamically calculate that range with respect to some error that you're monitoring for. Now, we say that when you want to quantize, you aim for weights and biases for quantization. And like they are basically more prone to quantization. But one thing also that you need to keep in mind is comparison between weight and bias. If you think about for a large model, for example, biases, the number of bias you have, they are normally in millions, right? Because you have one bias that's being shared in different locations. But when it comes to weights, you have billions. So what does that mean? You have a bucket of weights, like in billion, the other one is in million. So I don't need to worry about bias too much. I can just quantize them maybe from float 32 to float 16. But weights is where I need to spend my time for quantization, because a reduction from 32 to 16 in billion parameters, it's much more important than in compared to in million parameters. So that's that one. So I think that goes back to a question that one of your friends over there asked before. if I'm quantizing what should I monitor for and how should I monitor. So you can basically optimize the quantization process by looking at some mean square error between the quantized and the original. You don't want them to be far from each other. You want to quantize, but you don't want the error that, or even a scale divergence between quantization and the original weights. You don't want it to grow, because that means you're basically disrupting the model, or the model behavior will be ruined basically.
But the MSC we can only apply to like some kind of like problems, right? Not for every problems. Like this loss function is not applicable to all problems.
So no, you're looking at the weights, your weights, and the quantized version of the weights. It's numerical.
Yeah.
So you mean a square error, right? The error between weight and the quantized version is square, and you sum all of those across all your weights.
Just like we do with loss function.
Yeah. You don't want that number to be too high, because that tells you that there's so much difference between them. Or you can look at them as a distribution and do scale divergence between distribution of a quantized weight versus the distribution of the original weights. You don't want them.
Mean average error rate MAE rather than MSC over here. In that case, the number won't be that big, right?
That could be also. It's not like that these are the only techniques you can use, but you can figure out probably that maybe there's even a better way to do a comparison between the weights. It's just an idea of techniques that you can apply. All right, so then it comes to activations. The problem with activation is that you don't have them ahead of time. You will only get activation if you pass the data and data goes through the model. So that's when you get the activation values. So you cannot pre-compute those. Now, technically, if you see that's activation at each layer. Now, today you heard about a technique called post-training quantization, right? So post-training quantization means that I first develop a model, optimize it for whatever task you are doing. I get the highest accuracy. Then I bring this model, I'm not going to touch anything, and I just simply go bucketize the parameters. That becomes post-training quantization. So there is no learning in the process. You already have learned the model. You just simply go decide which layers you want to quantize, right? Which weights problems. You can, it's a neural network. You have access per layer. You can decide, okay, this layer, I'm going to quantize this layer. I'm not going to quantize, or you can just some sort of global quantization you apply. Technique like libraries like a PyTorch, TensorFlow, they all have that you can select per layer quantization, or you can basically apply the total quantization. The problem with post-training quantization is that it will reduce the accuracy of models, because you already trained that model and then you're simply just going to cut values, so basically kind of like change the dynamic range of values. So there are two forms of quantization that being used: dynamic quantization and static quantization. In dynamic quantization, when it comes to your activation, basically. So after on every neural layer, basically after the activation values, you sort those like this. You get the beta and you get the alpha per layer. Yes.
So, like in the initial lectures, you have taught us about batch normalization, right? So, will this be applied before that or after that? Since after, like, then our values will be normalized.
This is the activation. Activation is output of the model. Output of the layer or node.
Yeah. So after that, like we pass on to the different layer, then that particular output, if there are multiple hidden layers. In that case, I'm asking.
So when you do batch normalization, what happens? The input to every layer before it goes to the layer is kind of like it has a certain distribution, right? So here, you are not ruining the distribution, you're just reducing the points, like a floating point. You still get the distribution, right? You just reduce the number of points for the numbers within that distribution. By default, it's a Gaussian. It's always remain Gaussian. Doesn't matter how many points you are basically counting, right? So it still remains the same idea. It's just from the storage perspective or compute perspective, you're just reducing that floating points. So for every layer, output of every layer, you basically find this alpha and beta, and you use the same technique that you saw before. And every layer you do quantize, and pass it forward. So the activation basically For every activation, you find alpha, beta minimum. You apply some sort of like here, I think we did the dynamic range, which needed a 0 point. Remember, we saw S scaling factor, you saw a Z 0 point. Using that, you basically do the quantization and you pass it forward. And you repeat that for every activation. Right? And again, this is just activation. This is not the weight and bias. That already we talked about how to do dynamic quantization. In a static quantization, basically the idea is that you bring a data set. So you have a model already trained. You bring a data set called calibration data set. Using that data set, you calculate these statistics. Use that statistic for the calibration process, for the quantization process. So you basically assuming this. I have this model. I need a data set. This is a representation of a good data set. My model is going to see this data. You pass the data set forward. During the process, you calculate this statistic from this data set, and you store it for quantization. So as you go forward, you don't need to per layer to calculate this alpha and beta because you have pre-computed with respect to this calibration data set that you have. Okay. So now this days, and I think today Philippe also mentioned that we are going far beyond 8-bit quantization, right? And these days, the model basically have already pushed to 6-bit, 4-bit, 2-bit, and actually recent papers. We have a new models called bit quantization. You almost basically get rid of everything, right? And they prove that for certain domain, these models work, right? So it's kind of like everything presented in certain like a 1 or 2 values maybe. So on Hugging Face, there are 2 interesting, basically really good package or libraries that you can use. GPTQ and GGUF. If you want to quantize for GPU, you go with GPTQ. If you want to quantize for CPU, not quantize for CPU. So in basically GGUF, it allows you to offload certain weights matrices to CPU for the operation, instead of everything to be on the GPU. Okay, so there's a technique. I don't know if in this class we will get to over to that, but there's an idea of like you can offload certain operation to your CPU, use the CPU nodes for those. So that way you basically offload some process from the GPU because maybe you don't need GPU for that, and then basically you write it back or move it forward to the GPU. So GPTQ, and especially for 4-bit quantization, if you go on Hugging Face, when you search for a model, if you have a GPTQ at the end, it's 4-bit, like especially focused for 4-bit quantization. So it uses asymmetric layer-based quantization. That means for every layer, it uses the asymmetric. That means asymmetric was the one that you don't have a symmetric range, basically. And then you have a max and you have a mean, and then zeros will also shift all. So you basically apply something like that. But the main approach in GPTQ is that using a Hessian matrix and inverse of Hessian matrix. When you do gradient descent, what does gradient descent tell you?
The global minima of
No, okay. Actually, that's a gradient descent algorithm. Maybe I asked it wrong. First order gradient, Jacobian, switches down. If we do gradient descent, you take a derivation, right? What does that derivation tell you?
The slope is on the right direction of the minimum.
Okay, so what does the direction comes from the sign, but in general, what does the gradient tell you? First order gradient. Rate of change. What does second order gradient tell you? So second order gradient, basically, which is that Hessian matrix, it tells you about the sensitivity, right? How it's like a sensitive is your model with respect to certain direction. The first order gradient basically just gives you the direction, right? which is basically if you change this is the rate of change, and the sign of it basically becomes that direction that you get. So why every time you see optimization technique that they use second order derivation Haitian, why they converge faster? Because they use that cumulative knowledge that's basically rate of change. Like, okay, if I change this one and I go to this direction, I can go faster. So they reach to some local or global faster. Now, here basically in GPTQ, we use Haitian, and let's say for your weights, this is the original weights that you have. You calculate the Haitian and you get this, and you do inverse of Haitian 1 over this, and you get this. Okay. So inverse of Haitian tells you that how sensitive basically is the model output with respect to weights. How important is that weight? Okay. So now this is basically the process that happens. So let's say that was your matrix, right? So the first value was 0.5, and this is the inverse of Haitian. So in the original matrix, you pick the first, for example, in that row, you pick the first value, 0.5. You quantize it using it, for example, asymmetric 0 point, and int4 becomes this, 0.33. Then you dequantize it back again. The difference between dequantized and quantized version of the same weight becomes quantization error. You use quantization error as some sort of like a scaling factor for quantizing every point. Because you say that I know if I quantize, I have about this much error. So you use that as a way for scaling during your quantization. Yes.
Will those values, like we are like reducing the values to like lower decimals, will we use them while calculating our gradient? So in that case, like these values will be used later on?
No, this is post-training quantization. We already trained the model. You just go quantize the values. So there's no gradient, there's no learning here. Okay. There's like when the model is trained, you have a model, you just go quantizing. So this is like a GPTQ. Okay, so and then definitely take a look at basically, or look at, for example, EXL to or read on Hugging Face if you try to do quantization. If you want to go forward with quantization, take a look at the code examples. It's pretty useful. Yes.
Is this for the CPU or the?
This is for the GPU directly. Yeah. So the other one is GGUF, which is this one, which is for the CPU offloading. So GPTQ is well suited for running on full LLM. When you have lots of VRAM, you just want to quantize it. But this one, basically, the GGUF allows you to during the inference, you process like a certain operation or certain weights basically goes on your upload to your CPU, and then from CPU goes back to your GPU. So it's kind of like a shared process, Now, the GGUF kind of could work in this format. So if you have a weight matrix, like you have inattentions, imagine you have all these weight matrices. So imagine this is just one of them, one of those weight matrices. So within that weight matrix, within that all those weight values, you find S and alpha, a scaling factor and alpha. For example, alpha was the largest, and a scaling factor basically, depending on which algorithm you use, is it symmetric or asymmetric, there was a formula you suffered. Then you break down this weight into subblocks. Okay, this is what you see, subblocks. You could pass the subblocks on your CPU core. Every subblock, for example, goes to your CPU core. For a subblock, basically, you also will find an S, a scaling factor, and an alpha for that subblock. Then you can quantize in general, you can quantize that subblock using S times X. But what you basically will do is that the S, the scaling factor that you calculated over the subblock itself, will be quantized based on the scaling factor of the original matrix. So you offload smaller squares on CPUs, and for every smaller square, you find a scaling factor and an alpha for quantization. But you just change that quantization with respect to S of the large matrix that is on the GPU, right? Or the original basically matrix, weight matrix as well. So that becomes the, that's basically the process that happens in GGUO. And here is in this example, we're also using max quantization. So now all of this was post-training quantization. That means you develop the model or you have a model. But there is a technique called quantization-aware training, which the idea is that during training, you basically tell to the model that I'm going to use these parameters in a quantized way in the future. So I want you to learn the parameters somehow that after quantization, the impact of quantization is not high. So it's kind of like so the definition is that you build fake quantization during training. So later, when you quantize it, the error is not going to increase. Now, this is a general graph for a neural network, right? So quantized-aware training, this is like a convolution. There's a weight, input goes to convolution, there's a weight, there's a bias added, then you do activation, and you give an output. Quantization-aware training, it will add a quantization process after or wherever you inject basically. That's called fake quantization. Why fake quantization? Because the idea is that during the forward pass, data goes to basically layer comes out, you do quantize, dequantize. So what does that mean when you do quantize, dequantize? If your value, for example, was 5.2 and you did quantize to integer 4, and then you dequantize it, from 5.2, maybe you went to 4.5 because you got some quantization error, right? So 4.5 will move forward instead of 5.2, the original value. So during the forward pass, you are passing the fake or the basic quantized values forward. During the backward pass, during the gradient descent, you use the original weights for optics. So in quantized-aware training, forward pass happens with this process, fake quantization. Backward pass happens without that process. You assume that's not there. You just update the original weights based on the error that's calculated with respect to quantization. Does that make sense?
Yes.
Yes? No?
Because then we'll have vanishing gradient problem if you multiply small numbers of.
No, this doesn't add to vanishing gradient. So the idea here is that during the forward pass, let's say this is x is 5. And let's say it goes through something, and I quantize 5 to int 8 during the forward pass. And then I dequantize it back again. And let's say 5 or 5.82. And then let's say it becomes 4.32. So the difference between these two numbers is the quantization error. Correct? So this goes forward and so on. During the backward pass, I need to look at the error with respect to the original value, not this. Why? Because I am telling to the model, doesn't matter if this is 5.8 you have here. Later, I'm going to use this when I quantize the model. So you need to come up with your weights or values somehow that if I quantize, dequantize, the error is small. The quantization error is low. It can be as close as possible this way. Right? So it's kind of like you try to mimic the process of actually quantization happens, but it doesn't happen. Right? So later you have a model, then you go back and basically quantize the model, and hopefully that works in the same process. So quantization-aware technique focuses on two things in compared to post-training quantization. So in quantization-aware, if the error of the model, when you train a model, the purple FP32 that you see, it has a corresponding loss. On the right is post-training quantization. So the loss here is lower than this. That means if you train a model without fake quantization, you get a better loss, better accuracy. But when you quantize it as a post-training quantization, you end up with having something called, basically it's like a narrow quantization. You end up with much larger error when you do post-training quantization. When you do quantized aware, your final model from the global, like the optimized model, has a little, maybe a slightly higher error, but when you quantize it after, you get much lower quantization error. So quantized error training is a much better technique if you can implement during the basically training process. So now these days, lots of new papers actually coming. Every day is different. But one of the interesting ones is this BitNet. So the idea of basically this BitNet is that let's change the transformer process by doing some quantized aware, basically multiplication during any attention layer or any feed forward that you have. So anywhere that you do linear multiplications and there is some weights, in the BitNet, basically what happens, you use something called bit linear, which bit linear is simply linear multiplication that we do in transformer, but over bitwise bit quantized version of the weights. So during the forward process, you do quantized aware. That means you quantize the weights into a bit representation, and then you do your attention calculation. So it makes the model in general faster. Of course, less compute it requires. I can't speak to the accuracy or like a performance of this model, basically. But it happens. There are more coming out on this line of work still. So, and again, this is a one bit quantization. So everything basically goes to 1 bit. That's a really interesting thing. And this basically also another way that you can see it. Float 16 goes to, you do layer normalization, you do apps max quantization, int 8, and then you do using a 1 bit weight. Basically, the weights, all the weights are quantized into 1 bit representation. You do basically your transformer or attention, and then you dequantize and make it out. Right? And they work actually. They produce much faster transformer basically architecture. So now the next thing we're going to go over is the concept of pruning. So have you heard of pruning for neural networks before? You have heard pruning for decision tree, right? Or random, you go and cut the basically branches that's not important. So pruning in neural network is the same thing also. So you have a neural network trained, and what you do, you go prune it. Like you go get rid of layers, nodes that they are not useful. Okay. So the way that pruning, basically the idea is that the larger model, they need more memory, they're less efficient. Sparse models have less memory and are more efficient. One of the concepts in building a good neural network is enforcing sparsity within the model. The higher the sparsity, the better that model in the generalized that model in general, right? So what basically we do try to basically teach the models. So we have there's a process we see it now. You basically increase the sparsity like a 1 bit at a time, like a 5%, 5%, 5%, and you compare the results, and you have a basically threshold to drop. The main reason for this is there's a concept called lottery ticket. So the lottery ticket basically says that there's a chance of winning lottery, right? If you look at a neural network, there is a version of that neural network, one version of that neural network, a subnet of that neural network, pruned differently. That if you train it with the data okay, that prune version, that's randomly, that one basically initialization, will get same accuracy as the full that neural network. So there's one initialization, prune version initialization of this neural network that used in some data will get same result as a large model you trained over all of them. That's the idea of this laterally hypothesis. So the idea basically is that if you have a weight, there are a couple of ways that you can prune it, and this is just a couple of ways. There are actually more techniques too. On the left, you have the original weight. In the center, basically, we do 1 by 1, basically sparsity. That means you do 1, 1, and then you go here 1, 1, and then those two are flipped. It's kind of like a process. On here, on the right, you do 1, 2. You do a smaller square. 1, 2, 1, 2, 1, 2, 1, 2. So you basically drop those weights. You prune those by setting them to 0. So there are much more techniques on this pruning. We're not going to go over this. But Keras, for example, I don't know about PyTorch. Keras has a really interesting package for the pruning. So if you have a neural network in TensorFlow and you want to prune it, basically it's kind of like some sort of like a search. So you give a neural network to this model and say that, okay, you know what? I have a target sparsity. That means if you have 100 nodes and your target sparsity is 90, that means you want to drop 90% of those nodes. So you define a target sparsity for your neural network, and you let the model, basically the search, to go through. And you basically start by seeing impact of that drop. Over time, you basically improve as the pruning steps goes on, the sparsity goes up. So the interesting thing that you will see is these models, for example, Inception V3. The original model has 78%. These are large model, right? 78% basically, let's say, accuracy. And then we introduced a sparsity, 50%, 75%, 87.5% sparsity. And you only have a slight decrease in your accuracy. That means 87% of the nodes were dropped, and you just lost 4% of accuracy. Right? So if you look at the other ones, for example, here, you basically GNMT, you go to 90% sparsity, and your BLEU from 26.77 went to 26.19. So it tells you how much of these nodes and parameters of basically connections of the neural network are not useful technique, right? So in this scenario, so as far as this pruning process is how to get rid of this nodes. Now, before we stop, there was one question today that came up twice was it was about knowledge distillation, right? So the question that was asked was, what's the difference between knowledge distillation and quantization, or how do we do knowledge distillation in general? So if you want to do knowledge distillation, which the idea of distillation is basically extracting the most important knowledge from a model and giving it to another model. That's the distillation. So let's say you in the lab, you and your team build nothing works. You build a 70, billion parameters model. And you're like, this is perfect. It works really good. But we only can deploy 30 billion parameters model. But if we go to just train a 30 billion parameters model, it doesn't even compare with this. So what could we do? Knowledge distillation basically tells you that you have this one pre-trained, and you bring this one randomly initialized, not trained it. Then you bring a data. So data goes to this, at the same time data goes to this. This one is parameters are fixed, you don't train it, it's just forward pass. So it gives you some output. Let's say you're doing a next token generation. So the output is softmax, right? So for you basically get this softmax values per token, right? It's kind of distribution. Then this one, which is not trained, it also has two outputs. One output is just simply the softmax, the same softmax. The other one output is softmax converted to the actual token, hard value, right? Because you do hardmax over the softmax. Then this one, which is the actual token you predicted, this is a training data. You compare it with the training data, and you calculate the cross entropy loss. So you have a cross entropy loss, which is called hard loss, for exact token prediction versus what actually was expected. In this part of the basically pipeline, you need to calculate something called soft loss. So the idea of soft loss is that it's simply a Kale divergence. A Kale divergence between the softmax distribution from like a large model and softmax distribution from the smaller model. Your goal is to minimize this Kale divergence as much as possible. That means you are asking to the smaller model. You have two goals. One is to correctly predict next token, but you also need to be as close as possible to output of this model. So you distill the knowledge that this large model has learned, maybe over a larger amount of data, to this one. So this one is starting to mimicking the behavior of that. So this process is called knowledge distillation. Like the models that you see, mobile bird, like Albert, distill bird, those are all like doing some sort of like a distillation process.
So we minimize the soft loss, second one?
So we minimize both, this plus that basically. This becomes a combined strategy. All right. Okay, so I'm gonna stop here.